Hello and namaste everyone. Today I am going to demonstrate virtual lab which is assigned by UHD of Central Department of Physics, and I have choose the topic Michelson Interferometer, and my topic is determination of refractive index of thin glass plate by Michelson Interferometer, submitted to Central Department of Physics, Tirubani University, Kirtipur, Kathmandu, and it is submitted by me, Manjit Kumar, roll number 61, and I am batch of 2079. Contact number and email address is provided here. Here are table of content. First, there is objective lens, apparatus required, theorem, methodology, observation table, calculation, result, conclusion, and precaution. And here are the objectives in briefs. In Michelson Interferometer, first objective of our experiment is to alignment of a Michelson interferometer using helium and neon laser to observe concentric circular fringe. And second is measurement of wavelength of helium, neon laser, and refractive index of glass plate. And apparatus required laser light source, Michelson interferometer kit, optical bench, glass plate, meter scale. Brief introduction and history of Michelson interferometer. Introduction. The instrument based on principle of interference are called interferometer. They are basic optical tool used to precisely measure wavelength, distance, index of refraction, and temporal coherence of optical beams, etc. It is an amplitude splitting interferometer devised by Albert Michelson in 1890, the first American physicist to receive Nobel Prize for his work in optics. Michelson and Murray used this interferometer in their celebrated series of experiments designed to demonstrate the existence of ether. It is still an important instrument in today's laboratory and is being widely used as instrument for measuring the wavelength of unknown light source, to measure extremely small distance, and for investigating the optical media. And we come to the construction of Michelson interferometer. Construction of Michelson interferometer is shown in Figure 1. It is consisted of two highly polished mirror M1 and mirror M2, two glass plate beam split and completed glass plate are placed parallel to each other between the mirror at the angle 45 degree. The rear side of glass plate BS is semi-silver such that light from the source is equally reflected and transmitted by it. In this way, the division of amplitude takes place from the board source. Let a monochromatic light of wavelength lambda fall on BS, and half of light falling on BS is reflected toward the mirror M1, and another half is transmitted toward mirror M2. Hence, the BS is known as a beam splitter. In case of sources which are not monochromatic, the gas plate CP is inserted between EMS and EM2. The role of CP is explained further in the following paragraph. After splitting, the two rays are reflected by the mirror M1 and M2 and returned to the plate BS. The ray reflected from M1 is transmitted through BS, and the ray reflected from M2 is reflected again by BS. The two rays coming from the two mirror interference and fringe observed on the screen for laser or for by naked eye of neon lamp at E. Using one mirror is mounted on the translation stage so that it moves back and forth to observe the change in fringe. Optical path. The ray falling on mirror M1 and M2 are derived from the same source originally incident on plate PS. The wave reflected from M1 and entering the eye cross BC twice. However, the path of another wave falling on a mirror M2 in the absence of compensating plate CP travel totally in air. Thus, an extra optical path 2 bracket mu minus 1 bracket T is introduced, where T is thickness of plate and U is the refracted index of BS plate. For monochromatic light used. Presence of CP is not essential if fringes are produced with monochromatic light, but it produces a serious problem when white light is used. Thus, it is become necessary to compensate for extra optical path to mu minus 1 t for all wavelength. This is done by introducing another glass plate CP of same thickness as BS parallel to it. Thus, the two wave will interfere constructively and destructively as following condition of path difference delta. Delta is equal to 2 n lambda divided by 2, which is n lambda. For maxima, n is integer, and another delta is equal to 2n plus 1 lambda divided by 2 for minima. In contrast, Michelson Interferometer work on principle of interference, and I am going to elaborate through Wikipedia. Here we have a wave interference. The interference is a phenomena when two waves combine by adding displacement in single point in time and space. When one crest and trough are met, we have a destructive interference. When crest and crest of two wavelengths are met, we have a constructive interference, and this is the principle in which Michelson interferometer work. Constructive and destructive interference is caused by superposition of wave. When two waves are superimposed, they form interference, and here you can see interference of wave from 2-point source. Constructive and destructive interference are caused by path difference, which is done by two mirror. So another Michelson interferometer on Wikipedia. As our experiment is virtually demonstrated through this photo. Principle of Michelson interferometer. When we applied monochromatic light source, it strikes into half silver mirror which split light source into two parts, and it goes on two mirror and reflected back on same mirror. Then we observe from the instrument and measure the wavelength of light. Now we understand the basic principle of Michelson interferometer, so I'm going to demonstrate it on virtual lab. Here is our virtual lab, which is made by Amrita University, and I already bookmarked my topic Michelson interferometer and to find the refracted index of glass plate. And in the website you can find theory, procedure, self-evaluation, simulator, assignment, reference. So first I am going to discuss theory. The aim of this virtual life experiment is to determine the refracted index of thin glass plate, and the theory is already discussed. Thus, I'm going to state some formula and measurement of refracted index of glass plate. And consider a thin glass plate of thickness T and refracted index n inserted to the normal plate of one of two interfering beam in Michelson interferometer. The optical path length of same beam through the plate is nt, while the optical path length through a equal thickness of air is just t. So the increase in optical path inserting the plate is n minus 1 t. The beam transfers the plate twice, so the path difference will be t will be 2 minus n minus 1 t. If n is the number of frames displaced by inserting the plate, then n lambda is equal to 2n minus 1 t. And here our formula to calculate the refracted index of glass plate. An application of Michelson interferometer are widely used. Michelson interferometer are used in optical coherence tomography, CT, and medical imaging technique, and they are used in atmospheric and space application. And here the procedure for performing real lab to find the refracted index of glass plate. Align the laser source interferometer as described in the procedure to find the wavelength of light source. Place the rotation stage perpendicular to the optical path between beam splitter and movable mirror. Mount the glass plate on rotational stage aligned perpendicular to the optical path. When the glass plate is introduced, the fringe will be shifted and will be blurred. Make the fringe sharp again by moving the mirror mount with micrometer. Rotate the rotation stage slowly and count the number of fringes that occur as table rotates from perpendicular 0 degree to the angle. The refractivity of a glass slide can be calculated using equation 3. And there are procedures for performing the simulator. And I'm going to demonstrate my experiment through simulator. Here is our simulator. As you can see, and I'm going to demonstrate it. Let's zoom it. And you can find the power on, adjust mirror, adjust micrometer, thickness of glass plate, which is our aim to find is refracted index, and measurement. First, I'm going to turn on with helium lesion laser. There are many laser options, but helium laser, I'm going to use it. And let's power on. And we have very dim. So I'm going to adjust mirror and right amount intensify its brightness. And in our experiment, two things are critical. One is that knob, micrometer, and interference. We observe dark and bright fringe. Then we calibrate through adjust micrometer, which is, and I am going to adjust my micrometer very precisely, which is done with keyboard forward button. So to observe dark and bright fringe of our interferometer, and I'm going to observe the knob which is used to take readings for our measurement. So I'm very precisely going to demonstrate the experiment. First, and we're going to observe bright fringe and measure our reading through micrometer, and I'm going to change or adjust my micrometer and look the reading. So it is done precisely with keyboard forward button. Here is our bright fringe and we count order 10. So let's begin. 1, 2, 3, 4, 5, 6, 7, 9. Here's our bright fringe and we observe our micrometer, and then we again change micrometer or adjust knob. Here again we have bright fringe which is carefully observed. When we have that it is not counted at bright fringe, it is dark fringe. Again, we adjust our micrometer until we get bright fringe. Here our bright fringe, and we observe the reading, and it is done many times. So to get precise data from our virtual lab, here our bright fringe. Again, we counted the ions, we counted, and we take the reading from our micrometer. And I have done this virtual lab maintenance and written down my data. And in this micrometer, we have horizontal scale and vertical scale reading. There are two. For our perpendicular scale reading, we have to look that arrow, and for perpendicular scale reading, we counted this arrow. Again, we have bright fringe, and the our horizontal is scale reading is 2, and perpendicular scale reading is 5. And we again adjust micrometer. This cannot be counted as bright fringe. We adjust our micrometer until we obtain bright fringe and note down the reading from our micrometer. And the experiment is repeated again and again until we get observation as follow. And I have written down the observation. This is perpendicular scale reading, this is horizontal scale reading, and distance, and we have to count difference, and we have to take mean of difference and number of order, which is 10, which I counted 10 times, and we have obtained the wavelength, which I mentioned in my PDF. Here I have written down to find the wavelength, and here our calculated data, which our lambda wavelength of helium-neon region is 44 lakh 4,000 meter, and literature value for helium-neon laser is 632.8 nanometer, and this is for a wavelength of helium-neon laser, and I'm going to demonstrate refracted index of wavelength, which can be done through same simulator. So I'm going to enlarge same simulator, and here we don't have any glass plate, and I'm going to place a glass plate, and we have glass plate thickness of glass plate is 1 millimeter, and so on. We have 1.5 millimeter, 2 millimeter, and 2.5 millimeter, and 3 millimeter, and we can adjust angle of rotation of that glass plate, which is shown here, and we can show result. So I'm going to put thickness of glass plate as 1.5 millimeter, and adjust angle of rotation to 7.45 and show result. Then we have wavelength of source 5430 ms and refracted index of glass plate is 1.5, which is our objective of our experiment. And I already shown the refracted index of our glass in simulator, and there are precautions to be taken in account. And the precautions are: when turning the fine adjustment knob to count fringe, always turn it on one complete revolution before you start counting. This will be almost entirely eliminate the error due to the backlash in fine adjustment knob. Always turn the fine adjustment knob in one direction, either clockwise or anti-clockwise. Direct eye exposure to laser should be avoided. Observing laser interference fringe by reflecting mirror is prohibited, and avoid the touching any of the optics with your bare hand. These are the precautions to be taken in account. And we can observe fringe as follow. Measurement of wavelength can be done through this formula, where lambda is wavelength 2 and there is a difference or separation, and n is number of rings appear or disappear at center, and we can find lambda. And here is our result. Then we have find lambda and refracted index of glass. And last but not least, reference and appendix. I have taken reference from C.L. Arora, BSc Practical Physics, Yashchand publication, and I have used textbook of optics, which is also Yashchand, and wave interference, which is taken from Wikipedia, Michelson Interferometer, which is also taken from Wikipedia, and some by question I have attached on appendix. Define what is interference. Interference is a phenomenon that occurs when two or more waves meet and combine, resulting in new wave pattern. Depending on the phase relationship between waves, interference can produce either constructive and destructive interference. Question 2. What is the condition for interference? For interference to occur, two or more waves must meet and overlap in space and time. The wave must have same frequency. They must be coherent. Their phase difference must remain constant over time. And third question, explain the laser property and what do you mean by coherent source? The key property of laser light include coherence. Light waves are in phase with each other and their path phase difference remain constant over time. And fourth question, why are you using the laser source and why not bulb or sunlight tube or tape light? It is monochromatic, coherent, and highly directional. And fifth question, what is the role of semi-silver glass plate and why one keep it on 45 degree? The semi-silver glass plate is usually oriented at 45-degree angle relative to the incident beam. The orientation allows the incident beam to be split in two beams that travel along the path and they are perpendicular to one another. Sixth question, what do you think that semi-silver glass plate will look like? A semi-silver glass plate typically look like a rectangle piece of glass with partially reflected coating applied to one surface. The coating is usually thin layer of metal. Thickness and compression of coating determine the reflectivity and transmission property of semi-silver glass plate. Seventh question, what do you keep compensate plate in the path of light ray and is transparent in semi-silver plate to make the path of light ray equal and constant phase difference? Eighth question, is compensating plate of same thickness of semi-silver glass plate or it is different? It is the same thickness. Sixth question. Ninth question, what is the relationship between path difference and phase difference? The relationship between path difference and phase difference is path difference is 2 pi divided by lambda over x, and where lambda is wavelength of light used in experiment. Which one, and the 10th question, which one is fixed mirror M1 or M2 in Michelson interferometer experiment. In Michelson interferometer experiment, the mirror M1 is typically fixed while M2 is mounted on movable platform that can be adjusted to change the path length of same beam. And 11th question, M1 and M2 mirror are at 90 degree or more. The mirror M1 and M2 in Michelson interferometer experiment are typically placed at the angle of 90 degree with respect to one another. And 12th question, where image form usually M2 mirror by semi-silver glass plate. In Michelson interferometer experiment, the image of mirror M2 formed by semi-silver glass plate depends on the angle of incident beam on the plate. And 13th question, where the thin film of air form and how. In Michelson interferometer experiment, a thin film of air can be formed between semi-silver glass plate and the mirror M2 when the mirror is moved to change the path length of same sample beam. And 14th question, how one can change the thickness of thin air film when the mirror M2 is moved away from the semi-silver glass plate. The distance between plate and mirror increases. It creates a thin film of air between them. This thin film of air acts as a layer of low refractive index material, which can cause a phase shift in refracted beam that interferes with original beam by changing the mirror M2 position. And these are the questions that might ask in Viva. And and I have 15 question. How the light rays satisfy interface condition at P. The two light ray, one from reference arm and another from sample arm, travel different between path before they are recombined at semi-silver glass plate. The path difference between these two rays can be adjusted by changing the position of mirror M2. And that's the end of Viva question. And I have attached my photo. Name Manjit Kumar. Address is Sandhihar Karahanchi. Level MEC first SEM. Roll number 61. Contact number, email, and university email. All are provided with attached photo. And that's the end of Viva question, which is I attach in appendix and reference, which I have taken from many websites. Thanks for watching this video and see you next time. Bye bye.